All right, everyone. So let's get to this. Oh, you can't even see it. Here we go. Since we were just talking about this idea of limits and going to an infinite number of, I guess, repeating a pattern a certain number of times, let's start with the second half of this first page. Okay. Look at the lingo that I'm using. I use the word limit, so I hope you're getting a better idea of what that means. Identify that if you have a highlighter, I highlight this. This is what you will see on a quiz or a test. Identify the limit of the sequence. What does that mean? It means what does the sequence or pattern approach if you continued forever? That's what identify the limit means. So if you want to write that somewhere small, again, I'm paraphrasing this a little bit, but I hope it makes sense to you. Okay, I'll say it one more time. What does the pattern approach, or what am I going towards if I did this something again and again and again and again and again? Yes. Okay, except for you're jumping the gun. So it's good. So you're understanding already the idea of limits. Well, it's not as much mathematical in terms of calculations. It's a lot more conceptual. You have to really think about it. So I hope you can try. Here we go. First example. What does the pattern approach if you continued forever? Let's first figure out what the heck this pattern is. So, Nate, since you're here, what's the pattern?
It's getting divided. The decimal getting divided by 8.
So yeah, you can see it's getting divided by, or no, it's not divided, sorry, but it's not even mathematical. The number of zeros you see between the 8 and the 1 is
Increasing.
It's increasing. So if I did this forever, what would my final, it won't ever be final because I'm going infinity, but what would the number look like if we did this for a long time? 8.000000000000001. And if I did this forever, it might not be 0.0, it would be 0.00000000000 all the way to the n and then 1. It's so small and so close to 8. What number are we approaching? What is the limit? 8. That's it. Okay. So for this answer, the limit of this pattern is 8. How about I write that down just because it's the first example? The limit of this sequence or this pattern is 8. That's all you have to say. And it shows that you understand what the meaning of limit is.
Limit means like we go on.
Yeah. So the true definition is right here. If you take a look, oops. The true definition is a limit is a value that is approached, but not necessarily ever reached.
Oh, I see. So if it were to go on, it would be like 0.0000 getting 1.
Exactly. So 8.00 infinity 1 is almost negligible. So we just say it's 8. Good. How about the next one? There's no real pattern, but you might find these numbers familiar. I think I made a mistake. It's supposed to be 3.141, 3.1415, 3.14159. So if you knew some of those numbers, then you would have caught me. There it is. The limit of this sequence is pi. It's getting closer and closer to the value of pi. This is another one. This will really flex your strengths or your muscles on whether you understand fractions or not. I'm going to continue this pattern for you. 1.1/6, 1/7, 1/100, 1/999, 1/infinity. Ready? Yes, it's approaching. The limit of this sequence is 0. 1 over infinity, 1 over, let's say, a googolplex. Anyone know what a googolplex is? It's 1 with 100 zeros behind it. It's basically 10 to the power of 100. It's the largest named number as far as I know. You know, we have like a million, we have a billion, we have a trillion. I think it's the largest named number that we have. Even if we have such a large number, right? It will, if you divide 1 by that super large number, it's essentially 0.000. It's going to approach 0. That's it. Let's talk about this idea of limits and apply it to the concept of infinity. Okay, I'm going to clear this and move down. Okay, take a look. Infinity. A number set is infinite if it has no end and goes on forever. For example, a set of natural numbers is infinite. By natural numbers, I mean, 1, 2, 3, 4, 5. Numbers goes as far as you're able to count, right? So why does the limit of 1, 2, 3, 4, 5, 6 approach infinity? Yep. There's nothing, yeah, it's not. The sequence, yeah, does not approach any specific number. In other words, it will continue growing forever. So there is no actual number, it's just infinity. With that said, then, here's a challenge to you. Here's a challenge to you. Part B. Give me a sequence that goes to negative infinity. Write something. Let's pretend this was a quiz. Any sequence, it's open-ended. Make it approach negative infinity. What do you say? I'll give you 30 seconds. Write something here. Okay, so there's a bit of a shift in my presentation. So for people who are watching by video, bear with it. Write a sequence of numbers as a limit of negative infinity. Well, I could do 0, -1, -2, -3, ... Right? It could be, I don't know, negative, I don't know. Man, I'm at a loss here. It could be like, it could be something stupid like, this squared, this squared, this squared, right? This squared, whatever. As long as it's approaching negative infinity, it doesn't really matter. So I hope you understand the idea of infinity. Write a sequence of numbers that are finite as opposed to infinite. In other words, it has an end. Write a sequence of numbers that are finite. So in other words, tell me what an end is. You don't have to push it to the limit. It has nothing to do with limits. It's literally something like you could have written 1, 2, 3, 4. Done. Like that's it. There's no ... You see how there's an ellipse here saying it goes on forever? That was all it was. This question was just trying to show you, I guess, the importance of ellipses. Okay? So if you don't have it, it means there's an end. If you say ... it means there's something else coming on. That's it. What's that? What? Oh, yeah, well, just 1, 2, 3, and 4 tells me that's it. But this tells me you're going on forever, and so I have to understand the pattern if I want to push further. Okay, let's do it. Going to the next page, here are some examples. We will do these 2 examples and then talk about the idea of density before we quickly cover the history of math. I mean, we did this as a plug, right? Okay, Given 3n, what happens when n gets larger and larger? So again, assuming n belongs to a bunch of real numbers, wait, you won't even know that symbol, sorry. N is a real number. So if n gets larger and larger and larger, it goes to positive infinity. What happens to 3n? So look at the subtleness of that question. It says, given this, what happens? I never used the word limit, but I said, what happens if n gets bigger and bigger and bigger? That's another way of asking for the limit.
Wouldn't it be infinite?
No, it would, well, if n goes to infinity, then 3 times infinity is what I'm doing, which of course we wouldn't do it, but let's do a really, really big number.
No, you're not, like, what happens to the end?
No, the n is a number. N could be a 1, n could be a 2, n could be a 5.5. As n gets bigger and bigger and bigger, what happens to 3n? As in, what does it approach? It also becomes, I'm just multiplying by 3, it also becomes infinity, right? As n gets larger, you would say 3n approaches infinity. And I write the symbol because I'm too lazy to write INFINITE. Okay, too lazy. 30 seconds. So it really depends on how you look at numbers, right? What does it mean to get smaller and smaller? Does it mean becoming a 0.000, or is it becoming negative, 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 negative? Ellie?
I think it would be like negative.
Oh. Negative infinity? Do you have a different answer? No? Yes.
I'm actually so correct.
Correct. Getting smaller and smaller doesn't mean it's becoming more and more like a fraction. It does mean it's becoming more and more and more and more negative. So if this was a 0 and that was a number line, I am approaching negative infinity. So as n gets smaller, 3n approaches negative infinity. So it's a very straightforward concept, but it does require a little bit of practice because it's a different way of thinking, slightly different from the math that you used to know, but it's part of the same world. So let's talk. The last example, the last part of this lesson is going to, yes, is going to be, Ellie, go for it. You too. Okay. The last part I'm going to talk about is the idea of density. Quickly, please. Quickly. Okay, let's go. All right. Thank you. Bye. Patty. Okay, the density property. So the idea of density, again, is going to require a little bit of your creativity. Mike, you with me? Okay, I want to put that away if possible. Density simply means how dense something is, how many numbers are between these two walls. So if we were talking about integers, forget these real numbers. If I said, okay, integers are -1, 0, 1, 2, sorry, +1, 2, all the way to infinity, and it goes all the way to negative infinity. How dense are these two numbers? Are the numbers, let's say, 0 and 1? So in the world of integers, between 0 and 1, are there any numbers in between? I'll say it one more time. No, so I see yes and no. I hear both answers. I'll say it one more time. In the world of integers, are there any numbers between 0 and 1? No. So we're not going to call that dense. But now let's change the game. Between two real numbers, 2.4 and 2.5, how many numbers? Are there lots of numbers between 2.4 and 2.5? And the answer to that is yes. Why? Well, I could prove it. 2.41 is between those two. 2.411 is between those two. 2.4111. You get the point. Literally, between 2.4 and 2.5, there is an infinite number of numbers. Why are we doing this, Mr. It's hurting my head. I understand. But thinking sort of outside the box like this is also an element of math that is required if you are going to the upper echelon of things. So we're talking about it in grade 9 because you don't want to be blindsided when you get a little older. Okay, so with that said, this is the very top of the page, the very beginning. I went back to the start. Let's go back. How many rational numbers exist? So how many fractions exist? So if you want, this is fractions. So how many rational numbers exist between 2 and 3? Rather, forget the rational. How about decimals? How many decimals exist between 2 and 3? Yeah. Right? It could be 2.1, as I said, 2.11, 2.111, and I could have an infinite number of 2.1s before I get to 2.2, right? There's so many numbers. So how many rational numbers? There are infinite number. There is an infinite number of rationals between 2 and thank you. Jeez. Which brings us to the next one. So it's important for us to know the different kinds of number sets. Is the natural number set dense? Why or why not? And as a reminder, the natural numbers are the numbers you learn when you first are born. That's from 1, 2, 3. Density is literally how many numbers are between the two. If you're having a hard time grasping that idea, think of every number as like a piece of paper, okay? 2 is a piece of paper. 3 is a piece of paper. How many pieces of papers are between the two? And the more you have to stick between them, I think you'll understand what it means to be dense, to be packed. Question?
No, it's not what the number set is.
Pardon?
No,
Okay. So again, is a natural number set dense? Why or why not? The answer is no. Natural number set, the natural number set, or natural numbers are not number set. The natural number set is not dense because there is not an infinite number of values between between
Natural numbers, so you said like you're all ones you learn at when you're like at first, does that count like numbers that go past 100 or no?
it's one.
I'm wondering if
It's
it's
one to
like-
infinity.
No, yeah, correct.
Right?
The set itself will go to infinity, but let me clarify the definition. By definition, it's if you choose any two numbers, there's always going to be another number between. I'll say it one more time, okay? Here. The natural number is because if I choose two natural numbers, two adjacent, so two side by side adjacent natural numbers, there will not always be, there will not be a natural number between them.
But whenever choose one,
Okay, so infinity is not a number, so give me two numbers. Give me,
1 and 1 million.
okay, 1 and 1 million. Choose a number between it. Okay, choose a number between 1 and 1 million. 200. Choose a number between 1 and 200.
1 and 10.
Okay, so if I keep going like this, what are you gonna get? 1 and 2. Is there a number between 1 and 2? No. Correct. Pardon? Okay, go for it. Just make sure you keep this up. Take a review for your test. Okay. And so that's it. So the definition of being dense is if you choose 2 numbers in that set, you will always find something. That's dense. Yes. Yeah, go for it. Any questions? So that's today's lesson. It's a very conceptual thing, but it does require some, just some practice just to make sure you know what kind of questions are coming your way tomorrow. No. Wednesday. Sorry. Wednesday. Here's my expectation for you. On the back of this package, here, see you later. Okay. On the back of this package, you'll see a bunch of questions regarding limits, infinities, all the stuff for today. On the back of that page are exponents. And on this table is a big summary of all the stuff we did in Unit 1, specifically fraction stuff. So your main 3 big concepts of this particular test Wednesday is fraction stuff with BEDMAS, right? Exponent stuff with BEDMAS and whatever, and power rules and whatnot, and this funky idea of limits, right? I know we did scientific notation on Friday. Yes, that's part of the exponent business. So I hope you had to practice with that. The rest of class is yours. Please know this thing is what we're going to be working on tomorrow. I'm going to select random questions. If we don't have any requests, I'll just select some random questions that I think might be difficult or might be related to the test more than others. And we'll spend our time together that way. Hope you know what the expectations are. Any last minute questions? All right, you got all the time in the world now. Let's get to work. Go for it.